All right, welcome everyone. And we are going to get started with our FEA workshop. This is our third workshop. Reminder, if you haven't seen the previous ones, we do have recordings and slides posted from them for GrabCAD GitHub workshop and also the advanced CAD workshop. But for those who are here in person, thanks so much for coming. And we can get started.
Okay, so here's a quick rundown of the schedule for today. We'll go over what FEA is, why you should know about it, and how to set it up. We'll cap it off with a demo with like some really basic FEA analysis.
Oh, this particular GIF is unrelated. I just enjoyed it, but there will be some more, as always. All right, so right off the bat, what is FEA? FEA does stand for Finite Element Analysis, which I forget all the time, and I'm like, what is it again? But that basically means that it allows for the simulation of inputs on a part, so mechanical and physical inputs. Different programs have different capabilities, and we're going to focus on SOLIDWORKS today, which is, I guess, most commonly used, at least here at UCLA and in industry. So we're going to go over a couple of different simulation types: static, thermal, frequency buckling, etc. A lot of these are advanced options for very specific applications. So we're going to talk about some of the most basic ones today.
Okay, so I guess before we go into what FEA is, we should go into some background about it. Well, as Rebecca said, FEA is a way for us to simulate inputs on a part. Oh, it's okay. And why we simulate those inputs is so that we could check for failure. Because if you guys have taken the 156A course, you know how tedious it is to check, to like do everything by hand. FEA is basically that process, but in SOLIDWORKS or in your program. So really quick, there's a few theories like the Rankine, Tresca, and the von Mises theory. I believe SOLIDWORKS uses the von Mises theory to check for failure. And failure, at least the way that SOLIDWORKS defines it, is at the stress which a part begins to yield. So when a part has a load put on it and then it deforms permanently, that's when we define it as failure. And the von Mises criterion is basically simulating all those forces for a given geometry to see if any of the stresses exceed a yield stress. And if it does exceed that yield stress, it means the part has failed. SOLIDWORKS does this really quickly, and you can make it really defined. So it's just a very good way to, I guess, run this analysis.
Okay. So there's advantages of using this when you're designing, because it can be kind of intimidating and you might not know why you need it exactly or where to start, but it has some really serious advantages to do this in the design phase instead of waiting till prototyping to see if stuff's going to break. So you can really visualize, more than just knowing if something's going to break, where most of the stresses are concentrated and where the minimum stresses are. So your goal in this is to design your part effectively to minimize those places that are really high stress. So you want to fillet corners, reinforce areas of high stress, but you also want to know if you can do something like Swissing a plate, which is like cutting holes in it. So you want to know if you can do that effectively without creating too many high stress points, because you might want to do that to reduce your weight. If you do FEA, it will minimize your iterations because you won't have stuff breaking when you didn't expect it. And it's also just, even if you know that your part's going to be strong enough, it's just a sanity check to look at it and be able to say, okay, I know this is going to work. I know that there's nothing here that I have totally forgotten about, or there's no obvious weak point that I'm missing. So it helps you just to visualize that better.
Okay, so we're going to talk about how to set up an FEA. Really, all you need to do is define for a given part the part material. The material that you define the part with will determine its properties. So like yield yield strength, the elastic modulus. Those terms you don't need to know. All you need to know is, will I be using steel, aluminum, or even ABS? Just a fun fact, there's 2 different material types. I think it's good to know that SOLIDWORKS can model materials that are isotropic and orthotropic. So whether the properties of a part lie in a plane or if it lies in all directions, basically. You could also override a material's properties. So for example, I think ABS is missing its tensile strength. So when I had to run some parts for FEA, I had to put that in manually. But also, talking about ABS, PLA, PETG, keep in mind that running an FEA on 3D printed parts is assuming the best case scenario, assuming 100% infill. So it's not going to be entirely representative of how a part will actually respond to a load. So just be careful about that.
So one of the basic things you're going to work with when doing FEA is, before you start, you want to set up your fixtures. And these are defined as basically the mechanical and physical constraints or constants that exist in your system. Most commonly, you just use fixed geometry. So you just be like, this thing is going to be glued, or it's going to be bolted, or it's going to be very securely attached. I'm going to assume that it's unable to move in space. So you define that. You can see that in the green face that's highlighted on the right, is it's just been fixed, and then the rest of the part is free to move, but that face will never move or deform. If you have other different systems, you can use a roller slider, fixed hinge, and that just confines the motion of that part to what would be dictated by that kind of mechanical connection. There's different options for the geometry that you use. 90% of the time you use reference geometry, which is just you reference something that's in that's part of your part already, I'd assume. Yeah, and then the fixed faces is kind of was described before. Someone's calling me.
Okay, so once you define your fixture, you need to define the load. So loads are basically just the inputs that you will apply onto your part. There are many load types like torque, force, pressure, even temperature. Though we won't get into most of them, we'll only get into force and torque. Basically, when applying a load, you need to determine its magnitude and determine its direction. Also, its position onto a part. You'll see this a bit more, I guess, accurately when we go through the demo later. But I just want to note that you could also create a non-uniform distribution of load. So say you have a table and there's like, I don't know, a heavy backpack on one side and a cup on the other. You could kind of simulate that with a non-uniform distribution. We also won't be going over that, but it's useful to know.
Okay, so an important part of doing FEA analysis is defining your mesh. A mesh is an approximation of the geometry that you've designed in SOLIDWORKS. So it basically separates into polygons, which each have fixed points. And then the computer will basically apply forces and equations to each of those points in terms, which it can't do as easily if it's dealing with like a solid representation of your object. So it wants to split it up into simpler geometry. And you can tell it what resolution you want your mesh to be is basically how accurate and how like densely broken up your part is. Standard is equal resolution throughout a part, so it's all areas are considered relatively equally, but that might result in detailed areas losing their definition. So you can also do a curvature-based mesh, which will concentrate the resolution on the curved surfaces, which are going to be probably more detailed and intricate parts of your design. So keep in mind, if you increase the resolution, it's more computations. It takes a lot longer to do on your computer. So you want to balance that with how accurate you need your result to be.
Okay, so once you actually define your fixture, your load, and your mesh, you could run the FEA, and out comes some different FEA plots. So here are some defining quantities that you should look for. it's gonna spit out a stress plot, a displacement plot, and a strain plot. The strain one's not pictured here, but I'll go over it more in detail later. But basically, the stress plot, you can see on the top right image, it just shows you where stress is concentrated for a part through colors. But when looking at a stress plot, you could see like in the blue there's no load that's being passed through those the edges of that bracket. So you could probably save weight by switching it a little bit over there. Thinking about where your maximum stress is and your minimum stress is gives you an informed decision on how to make a part, right? To like switch some parts or switch a location on a part or bulk up another corner, say, with a fillet so that stress is distributed more evenly. The bottom right image, you'll see the displacement plot. We don't know if you don't know if you want displacement, but most of the time you wouldn't. But if you did, this displacement plot will show you like, oh, hey, the edge of this cantilevered beam will deflect the most. And it's good to know because sometimes you don't want a part that's going over, say, 1/10 of an inch. You could also create a factor of safety plot. This will just basically be analogous to your stress plot, but it'll show you the FOS, the factor of safety of your part. And it's good to see like, oh, hey, my part will fail first here.
Okay. You can also perform FEA on an entire assembly. So this is going to be a bit more complicated because you have to take into account how those parts interact with each other, as well as how individual parts are going to be formed. But it is really useful because most of the time you're dealing with assemblies and you want to see how parts are going to interact. So in order to do this, you need to start with your assembly already mated and fully defined, just so that you are basically giving it the most information about your system as possible. And then when you're doing the assembly FEA, you do it through connections between your parts. So you would add bearings, bolts, pins. Bolt is basically really similar to the fixed face that we talked about earlier. So it's basically just saying this part is bolted to this part. They're not going to move like between them. And then you want to analyze other areas of them or how they move as a whole. So this will provide a result that you can see on the entire assembly level, but it does take significantly longer because it's more parts.
And lastly, some tips. You could define a plot range in SOLIDWORKS at least to kind of show different colors, different orders of magnitude on, say, a FOS plot or a stress plot. You could also use mesh control to specify where you want more defined resolutions to be, say on a fillet or a chamfer. Deform result is basically it deforms the areas that have the most load. So say in a stress plot, the red areas would be deformed and you could visually see, oh, hey, this is where it's stressed out most. You could also use a compare results function to look at the displacement, stress, and strain side by side. I'll go over this a lot more later.
Okay. Here's some videos. Very good to watch videos. It's how I learn this kind of thing best because it's difficult to remember the names of different commands and things. So watching these, and then if you are trying to do it yourself later, having them to refer to as reference is really helpful.
Okay, so it's demo time now. I'll go over the stuff listed here, and I'll share my screen right now. Can you guys see the screen?
Yeah, looks good.
Okay, so the assembly that I'm gonna be running the FEA on today is basically a bracket with a hook on it, and we're gonna be applying a load down on the hook. Say you put like a really heavy backpack on it or something, and we'll be seeing how this bracket will respond. So first, I guess I'll go over FEA on the part level first. So I defined this material already to be aluminum out of 6061 alloy, but say there was no material defined. What you would do to define a material is on the right side here, see material, you could edit it. And in SOLIDWORKS, it gives you a whole gigantic list of different materials. You can see steel, aluminum, a lot of plastics too, so you can see ABS there. But for today, we'll be using 6061 alloy. And here you could see the different material properties. Okay. So to run an FEA, you're going to go to add-ins and make sure you have SOLIDWORKS simulation selected. Once you have that selected, you need to create a new study. When you select that, you can see all these different options. Most of them are kind of omitted right now because we don't have the right, I think, add-ons for them right now. But we could do a general simulation, which is static, which is what we would do most of the time. You can see on the right side here, connections, fixture, external loads, mesh. We won't be worrying about connections in a singular part FEA, but in an assembly level FEA, we would need to define this. So the three main parts to an FEA is the fixtures, the load, and the mesh. I'm going to define a fixed face first. You can see there's a bunch of different fixture types. This bracket will be bolted into the wall through these two holes. I would put a fixed face on the back because I don't think that'll move, but I think it's more accurate to select instead the whole faces because I know that's where the bolt will be. Okay. You could also see that there's a bunch of different options. Use reference geometry is what we talked about earlier, which is basically the default fixture type. But a bunch of different reference geometries that you probably wouldn't use for our purposes at least. So make sure you have use reference geometry selected. Okay. All right, now you can see those green arrows. These green arrows basically mean that the face is fixed. When you have that done, you could right-click loads. Again, bunch of different input types. We'll be having a force down on this hole. And it will be a force. So click force. You could select normally it has a normal direction to the face, but we want it to be in a selected direction. I'm gonna click an edge so it could go along this axis. And I'm gonna reverse the direction because, well, the load's going down. Let's say our backpack's really heavy, so 100 newtons, like 10 kilograms. Okay, so that's the force inputted. And so mesh. So this is by far probably the most complicated thing you'll need to do. So by default, when you run a mesh, so right click, create mesh, you could define its density right here. And this is basically the standard mesh. You could also run some parameters. So there are three to choose from: standard mesh, curvature based, and blended curvature based. The difference between the last two is that you could kind of define the polygon size a bit more in depth. But for our purposes, we'll be using curvature-based mesh, and probably that looks okay. A lot of it's like done by feel. Also, I'm using a good computer, so I could run a more fine mesh. Hopefully, you could see that the polygons in the hole is a bit more defined than the ones on the outside. In SOLIDWORKS, meshes are based off tetrahedrons and not, say, hexagons or other, or like squares in other programs. So just one thing to note, it's a fun fact. Okay, so we have the fixture, the load, and the mesh defined now. We should be able to run the study. So I'll run the study. And out comes some plots. So when you see the plots, SOLIDWORKS displays three main ones: a stress, a displacement, and a strain. You can see on the stress plot, it's very useful to visualize how the load pass looks in a part. So we have a load here, and the load is being passed through and concentrated at this corner. You could kind of tell that we should probably have a fillet here so that we could distribute this concentrated load more. That's why when you see brackets on a McMaster, they all have fillets because there's this stress here. We could also see that there's a large stress here on this hole. That's because, well, you could kind of visualize when you push down on this edge, it'll come down and hit the bolt first. I want to make a comment that this also lets you make an informed design decision. You could see here that there's basically no stress on this edge and this edge, so you should probably like Swiss out a little bit of it, just to save weight. And yeah, add a fillet here to distribute the load more. You can see the displacement plot. Here you can see that, as you would expect, the edge of the bracket falls down the most, and there's basically no displacement on the fixed holes. So the displacement is basically like the strain, except strain kind of shows you the parts of our geometry that kind of experience compression or tension, or it'll stretch. So displacement and strain, though they might sound like they're related, they're not really. You can see like strain tells us that this top face will stretch a little bit as well as this hole. But displacement will tell us, oh, but this will move the most. But yeah, you could also define a factor of safety plot, which I'll do right now. You could right-click on results for this. So when I define it, you'll see that the whole thing's basically red. That's because most of the part has the same factor of safety of about 1.7. Usually you'd want a factor of safety of above 1.5 for whatever you do, but it depends on, whether you're working on, I don't know, a robotic hand or a car tie rod. But here's a good example of plot range, what I talked about earlier. Let me edit the definition. Okay. Oh, wait, I think it's chart options. Yeah, okay. So right here, you can edit the range at which it shows different colors. So if I put, let's say 10, we can see that the factor of safety would go up. But here is where it's weakest. So yeah, it's a really far drop, but you could kind of see as I increase it, you could tell which point has the most stress, which you could tell earlier, but it's there for your reference. So that's FEA on a part itself. I'll now go over to FEA on an assembly. Go over here. So we have this hook, and basically we'll be doing the same exact thing, except we'll be connecting the hook to the bracket. So to do this, it's the same. You run a new study, static, except you need to do something which is connections. You need to find a connected face. So you go to contact set, and you choose the face at which it touches another face, basically. So I'll choose the top of this rack and the bottom of this bracket. And you can see that if you could allow penetration, that means they could go into each other. They could be bonded, but we'll put no penetration because it doesn't penetrate. Once we do that, we need to define the bolt that goes through. This is done with a connections type. You can see spring, pin, bolt, bearing, a lot of different types, but we'll be going into bolt today. Once you're in here, you can see counter bore with nut, countersink with nut, counter bore with threads, and countersink with threads. These 4 are what you'd be using mainly. So I plan on tapping this hole and putting a screw through to fasten it into the hole itself. So I'll do counter bore screw. You need to choose your starting face. So that's this edge. And you need to choose the face that the screw will kind of screw into, which is that edge. Once you do that, you need to define a preload. Well, you don't need to, but it's helpful to kind of simulate accurately. So I looked this up for general quarter 20 screws. It's about 8 pound-force per inch. And yeah, I defined the preload, and we could run the FEA, or we could define everything else. So let me do that real quickly. Fixed geometry, as I said before, these 2 holes. External loads. The force will not be on this hole this time. It will be down on this face where we hang our load on. So let's say 100 newtons. Okay, and then normal to that face, looks good. And we have a mesh. Create the mesh. I'll just use a standard one for now. Okay, and now I guess I could show you guys a useful tip, which is apply mesh control. So right now the holes for this one, and that one are kind of defined the same as these flat faces. I want them to be more resolute. I guess I'll just do those 2. You can make it as fine as you want, so I'll put it a bit more fine. And when I hit apply, these should, when we rerun the mesh again, should be fine. Okay. All right, so we have the fixture defined, the load defined, the mesh defined, and we have our connections defined. Now we could run a mesh on the assembly level. So I'll run the study. You can tell like it's taking a lot longer now because it's on an assembly level. Like a lot longer.
Hooray for SolidWorks plus Zoom. It's just a really great pair.
Yeah.
It's excellent for computers. No problems ever.
Never. If I were using my laptop right now, I think it'd explode. But so we'll wait for this to run.
Oh, we have a question. Someone's asking, what's a preload?
A preload is basically the torque that you define for a bolt. So whenever you screw in a fastener, say like a socket head, there needs to be a load on that screw so that it stays in place. So that's what a preload is. It's the torque required to screw it in and have it sit in place. If you set 0 to the preload I put on earlier, you could still run the FEA, but it won't be as accurate. It'd be treated as a pin instead of a bolt. Does that make sense? Okay, I hope it does. Okay, so you can see we ran the FEA and it's on an assembly level. Ooh. You can see that most of the stress is put onto this face of that rack, as expected, but it's good to know, like have a sanity check that this is indeed where the maximum stress is. You can also see the displacement. You can see that the bottom of the hook will displace the most. You can see that even though this is symmetric about the right plane, there's more displacement on the right side of the hook. this is due to that preload I was mentioning earlier. Okay, and you can see strain. So the strain will kind of tell you, oh, hey, this face of the rack is going to stretch the most. And again, these faces will stretch as well. So you can see deformed result. If I went to a side view here, if I click on deformed result, it goes back to normal. I can turn it on, comes back. I could edit it. See if I can edit it. Yeah, okay, so deformed shape, if I made it automatic to what its number actually is, you can see it kind of automatic, good. Yeah, you can see it kind of displaces a lot more. You could tweak this to see like how much you want to see the strain, stress, or displacement. You can also turn it off if you don't like how it looks, but I find that it's helpful to have, at least on a true scale. Okay, and the last thing I want to talk about is results, compare results. This is just a good way for you to compare all of your different results at once. So if you're presenting something, you could kind of say, oh, hey, this is how much stress there is. It matches the strain and displacement plots. And if we had a factor of safety plot, we could say, oh, hey, the lowest factor of safety is 1.7, which I think is acceptable for our uses. But yeah, that concludes the FEA workshop. It's not very in-depth. I just taught you guys how to run a FEA on a static part for static loads. Normally, if you want to go more in-depth, that requires a lot more computation as well as understanding of it. But for our purposes, when looking at the load on the chassis or on the launcher, this should suffice. But yeah, that concludes the workshop or the demo portion of the workshop. Are there any questions? Yeah, so the bolt connection can simulate stresses on the bolt, but you need to import a bolt from a library. I didn't do that because I don't have that library installed, but you should be able to. I'll include a link on how to do it later when we send out the recap of this workshop.
Yeah. Yeah, we can continue to take some questions. Just really quick, wrapping up this workshop, here's some ASME information. As always, we have 2 upcoming events, ASME class planning this Friday, and also a trivia night next Monday, and those are going to both be through our Discord server. Here's our usual links of how you can contact us. There are a few other events that were on our newsletter that aren't mentioned here, so I suggest you check those out, though these are the most central ASME events. And houseplant fun slide for questions.
Yeah, if you guys have any questions, feel free to ask. If you don't, you guys are free to go. Thanks, guys.
Yeah, thanks, everyone.
Yeah, good night.